apply some F equals ma on some particles. So point-like particles are very small. We cannot see them. This is a lot of particles, but doesn't look like one. But if you go to space and look at our solar system, this is our sun. You can see there's some planets orbiting around it. And at the scale of a solar system, our planet is just a point. It's just a particle. So now I'm going to say that Earth is just a particle, and Sun is also a particle, so we can study some motion between particles. Okay? Alright. So when you look at the orbit of Earth between Sun, you know it needs a acceleration because it's doing circular motion. If you want acceleration, you need to provide a force, but there's nothing connecting Earth and Sun. I mean, I don't see a big string going up into the sky holding Sun and Earth together. So Newton came up with this idea that if a particle and another particle is some distance away, they can still have attraction force between each other, and this attraction force exists for every single particle. There is a universal attraction between particles, and he called this gravity. Now, gravity is a force. Let's say the magnitude is Fg, and it should be attracted. We know that Newton's third law tells us the interaction should be symmetric. These two forces that they exert on each other should have the same magnitude and opposite direction. And to get you guys more familiar with vector notation, I can set my coordinate system at here. Then the position of the first particle will be this R1 vector, is the position. The position of this other particle will be this R2 vector. And if I want the distance, I can subtract them. I hope you've done your homework. If you do subtraction, you know you'll get an arrow pointing from here to here or here to here. It doesn't matter because we don't want the direction. We want the distance. So you take the absolute value, and then you get just the magnitude of this distance, and I call it R12, and that will be the distance between these two particles. So we know there's a gravity exists, but what should it depend on? Gravity is a force. Force is frame independent. Therefore, if we want to write down a formula for it, we can only use some quantity that is also frame dependent. One such quantity is the distance. The distance between these two particles is the same no matter which frame you're in. So we know gravity should be somewhat related to the distance between particles. We don't know how exactly it's related, so let's say it's related to the power of n. We don't know if n should be 1 or 2. We don't know if it should be inverse proportional, inverse square proportional, or something like that. But we know it should be related to the distance. Anyone don't recognize this proportional symbol? Proportional? Good? No, good. If I roll it as an equal sign with some concept here, are you happy?
Does the thing just mean like proportion?
Yeah, that's proportional.
Okay.
So I mean, keep using that. Proportional means that if y equals x to some number here, then we say y is proportional to x. If y equals x, y is proportional to x. If y equals 2x, it's still proportional to x.
Okay.
If y equals square root of 3, it's still proportional to x. As long as you get a straight line, when you plot y against x, then this is proportional. And we don't really care about this constant right now, so we write it as proportional instead of equal sign. Okay? Now, if this is x squared, y is not proportional to x. Y is proportional to x squared now. If I plot y to x, it will give me a curve. But if I plot y to x squared, it will give me a straight line if y is proportional to x squared. Now we know gravity is related to the distance between particles, but we don't know how exactly it's related yet. So I just write a number n to represent the power of distance. And there must be some constant, but let's not worry about that right now. Okay? So I wrote it in the denominator because when two particles is very far away, there should be no interaction between them because it's too far, they cannot communicate. Therefore, we know if the distance is bigger, gravity should become smaller. That's why I put it in the denominator. Okay? But we learned that if I throw a thing, the acceleration of a thing is always g to the ground. No matter how heavy a thing is, the effect of gravity on it is the same. The acceleration it gets from gravity is the same. In order to do that, we look at Newton's second law. Acceleration from a force is the force divided by mass. Therefore, if we want this to be a constant of mass, then the force over here must be proportional to the mass of the particle itself, so that the mass can cancel, and the acceleration on an object will be a constant no matter how massive that object is. Therefore, we know that gravity should also be proportional to the mass of one of the particles. Does that make sense? If gravity is proportional to the mass of m1, then the acceleration that gravity causes on m1 will be the same no matter how heavy m1 is. No matter how massive the particles are, the acceleration will be the same if gravity is proportional to the mass. So they cancel in Newton's second law. Okay. Let me just give you a more precise example. If you are near the ground, I will tell you later that if you are near the ground, gravity will be the mass of this ball times a constant acceleration g. So if you look at the acceleration of this particle, it will be the force divided by the mass, and you see the mass cancel. So no matter this object is 1 kilogram, 2 kilogram, or 3 kilogram, you saw the feather and the bowling ball thing. You drop them, they fall down with the same time because the acceleration caused by gravity is the same. Therefore, gravity must be proportional to the mass of the object. So you can cancel that in Newton's second law. Okay? Yes?
Constant acceleration because it's always g?
We know it's always g, and we show that experimentally with solar can or feather and bowling ball. So from this experiment, we know that gravity should be proportional to the mass of the object it's acting on, so that the mass and the mass can cancel, and it will not affect the acceleration of the object. Okay. So now we know it should be proportional to the mass of the first particle, but wait. Gravity is affecting m1 but also m2. If m1 should have an acceleration independent of its mass, m2 should also have an acceleration independent of its mass. This interaction, I can draw the same argument on the outer particle and tell you that the mass of the outer particle doesn't affect the result too. Therefore, it should be proportional to both their mass, not just one of them. We need to make it symmetric. because interaction is symmetric. Does that make sense? Okay. So we know gravity will cause some acceleration independent of their mass, and it is frame dependent, so it should be proportional to their mass and some relation with the distance between them. Okay? So how do we figure out this power? We have to do experiment because so far there's no way in this course we are going to tell you that n equals 2. If you're Einstein, you can get n equals 2 from curvature of spacetime, but we're not doing that. So let's try to compute something we can predict or something we can measure in experiment. We know that the planets are moving in circle. To be precise, they should be moving in ellipse. That is called the Kepler's first law, but we are not doing ellipse in this class, so we just assume they are all moving in perfect circle. The Earth actually has an orbit very close to the perfect circle, so it's fine. We are going to look at the motion of Earth in the sun's frame. In the sun's frame, the sun is at the origin. So the Earth is going in circle with some speed like this. Now, before we do F equals ma, we need to satisfy the first law. Is this an inertial reference frame? If we look at that diagram, gravity between Earth and the sun should be the same. So if Earth has an acceleration, sun should also have an acceleration. But when the force is the same, acceleration is inversely proportional to the mass. If you are very massive, then the acceleration caused by